In this video, we're going to talk about shear stress. The equation for shear stress is tau equals, for a circle, it's 4v over 3a. That's for a circle, circular cross-sectional profile, that is, circular cross-section. And then for a rectangle, tau equals 3v over 2a. That's for a rectangle. Now, you might wonder sometimes where these equations come from. They can actually be derived with a little bit of, I think, some calculus probably. It's not something that you ever really need to know as a mechanical designer. It's an interesting exercise. Honestly, I haven't done it ever since I was, in college, and I've never needed to do it. So it's not something that you need to know. But if you're ever curious, these equations can be derived. They're not just, plucked out of thin air. So let's see, going back to shear stress, just like bending stress or stress and tension, the reason that you might want to calculate shear stress is to compare it against your shear yield strength and determine whether or not you're going to have a failure in shear. Now shear, let's say that you've got maybe we don't want to do a cantilevered beam this time. Let's say that we've got a rod. So we're just drawing half of a rod. And let's say that, here, let's draw a screw. We've got a screw. And this screw is, let's say that half of it is in this blue block like this, and okay, sorry I keep changing things, but this is a shoulder bolt. So let's say it's a shoulder bolt, right? So we've got just our shoulder right here, and then we've got a threaded end over here, and half of this shoulder bolt is in this blue part, and then the other half, let's say, is in this green part. And then this green part is it's fixed out here somewhere. And then let's say that we have a load that's placed on this blue part right here. So this blue part is being pulled down, and the only thing holding the blue part to the green part is the shoulder bolt, which means we're creating a shear force right here in this area, right? Because it's the end of the bolt is supported by the green down here, right? The bolt is being kind of pushed down into this area. And then the other half of the bolt is being, or I should say, the far half of the bolt is being supported, pushed down and supported by this area. So really, this green part is pushing back up on the bolt, in the shoulder screw in this area here, and then the blue part is pushing down on the shoulder in this area, and that creates a situation called shear. This is the definition of shear, where you have forces acting in opposition to one another that are adjacent to one another as well. So this is a shear example. Now let's say that we wanted to determine whether or not this shoulder screw was going to fail in shear. So a few things we need to know. We need to know the diameter of that shoulder screw. Why don't we just say the diameter equals, let's say, 1/4 of an inch, 0.25 inches. We need to know what the shear stress or the shear force is. So let's say the shear force equals, how about 250 pounds of force. And then we need to know what the shear yield stress or the shear yield strength is. And it's something that you can look up. It's, I think, less common to find than just your yield strength. And so kind of like a shorthand or a rule of thumb or a shortcut to getting your shear yield strength, if you can't find it directly in a table, what you can do is say that your shear yield strength is going to equal 1/2 of your your tensile yield stress. So 1/2 of tensile yield stress. So if we know that, let's say this is a stainless steel shoulder screw, and maybe the tensile yield stress is, I don't know, 50,000 psi or 50 ksi. Let's say tensile yield stress or strength equals 50 ksi. Then our shear yield strength is going to be 1/2 of that, so it equals 1/2 times 50 ksi equals 25 ksi, or in other words, 25,000 psi. Okay, so now we know what our shear tensile strength is, and we now need to calculate the shear stress in this bolt. All right, so since it is a bolt, it's a circular cross section, so we're going to use this top equation here, and we're going to say tau equals 4v over 3a, and that our area, our cross-sectional area, right, cross-section of that shoulder bolt, and it's going to be at the shoulder right here. So this cross-sectional area right there, so that's going to be equals 4v divided by 3 pi r squared, or pi d to the 4th over 4. Well, let's just use pi r squared. Let's keep it simple. Okay, and then that's going to equal 4 times the shear force is 250 pounds of force, divided by 3 times pi times the radius, which is half of the diameter, and our diameter is 1/4 of an inch, so the radius is going to be 1/8 of an inch, which is 0.125 inches. Okay, and if we do some math, that is going to equal, let's see, oh, I know, inches squared, that's why. I was looking at my pounds force per inch and thinking that's not right, but I just forgot to square. Oh, we did this wrong. Okay, that's why. 0.125 inches squared. The whole thing is squared, right? Pi r squared. Our r value, our radius is 0.125 inches, so we're squaring 0.125 inches. Okay, so 4 times 250 pounds, that is just 1,000 pounds force. And then down on the bottom, we've got 3 times pi times 0.125 squared. So that is 3 times 3.14 times 0.125 times 0.125 equals 0.147, we'll just say 0.1472. 0.1472 inches squared. And then when we calculate that value, it is, so we got 1,000 divided by 0.14, what was it? 0.1472. 0.1472 equals 6793.5. 6793.5, and that's psi. Okay, so now we have our shear yield stress, and we compare that to our shear we have we have our shear stress, which is here, boxed in, and we compare that against our shear yield stress, which is 25,000 psi, and 6793.5 is much less than 25,000. So we know that we do not have we do not have a condition in which plastic deformation will occur. So we are just fine with the 250-pound force applied to this shoulder screw. And that's how to calculate shear stress. You know what? Maybe one more thing that I'll mention here. The situation that we've described here, this is called single shear, because the shear is acting just in a single area, right? Right here where I'm circling, that's where the shear stress is acting. But we could potentially have another condition where, let's say we've got, I don't know, a block here, and we've got another block here, and we've got a pin, or whatever it is that's going through both of these, and then we have another block here, and this is a cross section that we're drawing. So we're looking at the solid material, but really that block in blue is just one single block that has a hole drilled through it. So let's see, if we were to draw that block in 3D, it would look something like this, right? With just a hole drilled through, and then on the other side there would be a hole there as well, and you've got a hole going all the way through. Anyway, that's what it looks like. And then in green, yep, we got some crosshatch on the green as well, because we're looking at just the cross section of the solid material. And all right, just to be thorough, we got some here on the pin as well. Okay, so this condition would be, and let's say that these green blocks are fixed to ground on both sides, and then the blue is what we have loaded, and we have, I don't know, whatever it is, 250 pounds there. Now, in this situation, this is called double shear, right? We have shear force acting right here and right here. So when we have a situation like that, we actually get to take our solution, right? I think we used 250 pounds before. Yep, 250 pounds. So let's say this is the same load, 250 pounds, and we have the same size. It's a stainless steel pin that's a 1/4 of an inch diameter. So really the same conditions, but now we're in double shear instead of single shear. And when we're in double shear, we get to take our answer and divide it by 2. So this 6,793 pounds per square inch of shear stress gets distributed equally across this area here and this area here. So each one of those areas only has, what is it, about 3,400 psi of stress there. Or I guess the other thing that you could do, it's the same thing. You could also double your shear yield strength, because it's working in 2 places now. So you could keep your 6,793 psi and say that now the shear yield strength is actually 50,000 psi, because you're in what's called double shear here. The numbers work out the same way either way. So anyway, that's the difference between single shear and double shear, and how to account for either one. If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer, or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.